So my talk is about a small R package called gdata.frame, which is a package intended to deal with group data, and more specifically to deal with data sets for which each observation is a combination of two indexes, or values of two indexes. So my interest in the subject was that I was working on two packages, a PLM package for panel data econometrics, when you have several entities observed for several time periods, and also my work on the mlogit package for random utility models or discrete choice models. And in this kind of models, you have different choice situations with several alternatives. And while working on these two packages, I found that there are some limits to describe the model I wanted to estimate using the basic formula data interface for two reasons. The first one is that often I wanted to define several sets of covariates, and the other reason is that most of the time I had to indicate the structure of the data sets. So there were two solutions. The first one was to add a lot of extra arguments in the fitting functions in order to completely describe the model I wanted to estimate, and the second solution I preferred was to provide enhanced formulas and data sets and data frames, which means formulas and data frames which can carry more information about the features of the model one wants to estimate and the structure of the data. So on the formula side, this result was the formula package, which enables to describe formulas with several responses, like here, and also, more importantly for me, to describe formula with several sets of covariates on the right-hand side, separated by the pipe sign here. So for example, using the formula package, you can estimate with PLM an instrumental variable regression using only one formula and the data argument, as if you don't have this formula package, you need to provide an extra argument here, which is a one-side formula containing the set of instruments you want to use. On the data side, on the data frame side, I wrote in the two packages two different functions and two different classes, which are called the pDataFrame for PLM and mlogit.data for mlogit. And I was very unsatisfied with this solution because there was a lot of code duplication, a lot of inconsistencies between both functions, and also a very weak integration with tidyverse, especially with tables and dplyers, because tables don't work for both packages, and dplyr functions, most of them don't work correctly neither. So just to understand the kind of data sets I'm using here, I start with two examples of panel data sets here. So this one deals with states, American states here. That's the first index. We have 48 states. The second index is year. We have 17 years. And obviously, each observation is a unique combination of these two indexes. And moreover, you have a third variable here, region, which nests the first index, because obviously every state belongs to one region. The second example is also a panel data example, which is called wages here. So we have information about 595 individuals for 7 years. We don't have any indexes in this data set, but we know that the order of the observations are sorted first by the individual index and next by the time index. So knowing just the number of individuals is enough to retrieve the information about the structure of the data. The next two examples are discrete choice models example. The first one here is the Rosky Transport dataset, which deals with the choice mode for to go from Freetown Airport, Sierra Leone to downtown, using one of the four available modes here. So the first index here is the last column, called here CHID, which is the choice situation ID. That's the first index. And the second index here is the mode column here, which indicates the different alternatives which are available. And this time you can see that this CHID, the first index, is nested in the ID index here. The ID index identifies the individuals. Okay? And as you can see here, we have the same ID for all the three first choice situations in this data set, which means that we have repeated choice, and that the first three choice situations here corresponds to the same individual. The last example is also a discrete choice model example. It's called the Japanese FDI dataset. It deals with Japanese firms who implement a production unit in a European region. So this time the first index is the firm here. The second index is the region. That's the alternative. And this time you have a nesting variable for the alternative because every region belongs to a country. So the small package I propose is just a standalone package with only one exported function, which is gdata.frame to define a gdata.frame object, and only a few methods. So the following principles are used in this package. It's suitable for data sets where, as we have seen, all the observations are uniquely defined by a combination of two indexes. We want to be able to introduce some nesting structure for one or both of the indexes. The indexes are stored as an attribute of the data frame. And finally, if we extract some series from the gdata.frame object, then we get a series which inherits the index attribute from the data frame it came from. Some other package which performs similar things, among all of them, Spacetime Ansible. So Spacetime Ansible also deals with data which are completely defined. Each observation is defined by a combination of two variables, two indexes. For spacetime, the first index is a spatial entity, and for both of them, the second index is a date. So to illustrate the use of the package, I will use this very simple dataset, which contains two economic variables, GDP and unemployment for 4 countries, France, Denmark, Italy, and UK, for 4 years from 2000 to 2003. So the first index is country, the second index is year, and both of them have a nesting variable because I have here the zone here variable which nests the country, Eurozone, not Eurozone, and I also have the period variable here which nests the year because 2000 and 2001 was the pre-Euro period, and 2002 and 2003 was the post-Euro period. So the basic use of the gDataFrame function is just to provide, of course, as first argument a data frame, and then a second argument which is an index. And index here is a list of 2 character vectors of length 1 or 2. Here, the first element of the list indicates that the first index is country, which is nested in the zone variable. And then the second character vector indicates that the second index is year, which is nested in the period variable. The result is the gDataFrame, which has an index attribute, which can be extracted using the index function, like here. And you can see that the index is a data frame which contains all the variables which have been defined as being either an index or a nesting variable for an index. And you also have here an IDS attribute which indicates that the first 2 columns refers to the first index and the last 2 columns refers to the second index. Of course, you can use gDataFrame with only one nesting variable. So for example, here there is no nesting variable for the first index, but only for the second one. And you can also, which is quite a current case, not define any nesting variable. And in this case, you just indicate either a list or a vector containing the name of the 2 indexes. Sometimes you only have one index in your data frame. The other one is implicit. So in this case, you can provide either the name of the first index and the nesting variable here, or only the name of the first index. And in this case, as you can see, in the index attribute, the second index is auto-generated and called here ID2. You can also sometimes use integer to define the structure of the data sets. This is the case when you have data ordered by the first index and then by the second index, and that you know that you have the same observations for any modalities of the first index. So in this case, you can just indicate the number of modalities for the first index, and then you get an index for which the two indexes are auto-generated and called ID1, ID2 here. Finally, you can provide no index argument at all, and in this case, it is assumed that your data frame, the first two columns are the indexes of your data frame. I wrote some special method for extractors for gdata.frame. For those ones which only performs extractions on columns, the only trick is to save for the result the index attributes, otherwise it's lost. And for this kind of extractions here, which deals with rows and with columns, you also have to make sure that the resulting index select the relevant rows and not the whole rows. There are also methods to extract series from a gdata frame, and there are two features here. The first one is that extracted series have a special class which is called here gSeries, and the second feature is that a series that is extracted from a gdata frame inherits from the index attribute of the gdata frame it has been extracted from. So this permits to write some methods, some specific methods for series. For example, in PLM, there are a lot of methods that are used to perform transformations on panel data. For example, there are lag and diff methods, which are specific because when you use panel data, you need to have not only an NA on the first position of the resulting vector, but you need to have NAs here for every first observation of every country. Okay, so that's a way to define simply some methods for this extracted series, and this method needs the information about the index to properly compute the lag here for panel series. Finally, I try to make the gdata frames works with some of the tidyverse packages, especially tables and dplyr. So here I just first coerce the Euro data frame in table. And if I use now the gdata frame and put this table as the first argument of my gdata frame, then I have, as a result, a gdata frame object, but which inherits for the table classes, and especially with prints like tables. And moreover, the index is also now a table and not an ordinary data frame. Finally, I try to make it work with at least some of dplyr's functions. There were problems with dplyr functions, with most of them at least, because a dplyr function returns either tables or data frame, and if the argument is a gdata frame, the result is not a gdata frame. So the class is lost, and moreover, the index attribute is also lost. So I had to rewrite some methods for gdata frames. As an example, this is the mutate method, and the strategy is the same for almost all the methods. So first, I save the attributes of the gdata frame here. Then I coerce it to a data frame, to an ordinary data frame or table. Then I use the default mutate method to this data frame here. And then I just modify the attributes that need to be modified for mutate. It's just here the names attributes that should be updated here. Then I link the attributes to the resulting data frame here, and I return it here. Okay, thank you.
Thank you, Yves. We have time for a few questions.
Yeah. Thank you, the author of Spacetime here. So I like your talk. I wondered, why did you choose to register the column numbers rather than the column names? Because if you provide mutate or some methods, then column orders might change.
You said column numbers?
Numbers, not names.
Do you mean here?
Yes.
Yeah. If I take this example, it's more interesting. I have here only one variable for index 1 and 2 for index 2, the second index and the nesting variable. So 1 and 2 here is just to indicate that the first one refers to index 1 and the last two to index 2. I don't know what kind of names I could have put there. Call names?
Column names.
What do you mean? What? You mean here I should have put country, year, and year?
Yes.
Yeah, okay. Yeah.
Okay. Thanks. We have time for one more question, please. No more questions. I'd like to thank Yves again.
Thank you.